Now let us continue with sequences, important questions. So take this one. Show that every Cauchy sequence is bounded. Very, very important. So first let us take Sn be a Cauchy sequence. Now we will choose epsilon is equal to 1. So when we have assumed Sn as a Cauchy sequence, let us write the definition of a Cauchy sequence. So the definition is there exists a positive integer m. There exists a positive integer m such that mod Sn minus Sm is less than epsilon. But epsilon we have taken as 1. So I am writing it as 1 for all n greater than or equal to m. So whenever we have modulus, we take minus 1 and plus 1. So we can write minus 1 less than Sn minus Sm less than 1. Now what we will do is we will add Sm on all sides. So we will get minus 1 plus Sm less than Sn less than 1 plus Sm. Let's say for all n greater than or equal to m. So now we can write minus 1 plus Sm less than Sn less than 1 plus Sm for all n greater than or equal to 1. This is equation number 1. So now let us take k is equal to minimum of these values. Minimum of x1, x2, x3, so on up to xm minus 1 and sm minus 1. This is equation number 2. And we will take capital K as maximum of x1, x2, x3, so on up to xm minus 1, sm plus 1. This is equation number 3. So from all the three equations, equation number 1, 2 and 3, we can say minus k less than or equal to Sn less than or equal to capital K for all n greater than or equal to m. Therefore, you can say that sequence Sn is bounded because it is within a finite limit. So take the next question. This is also very, very important. Prove that every convergent sequence is a Cauchy sequence. So let us say limit of Sn is equal to S and let epsilon be positive. Then there exists some n greater than 0 such that n is greater than n, which implies mod Sn minus S is less than epsilon by 2. Now clearly m is greater than n, which implies mod Sn minus S is less than epsilon by 2. Therefore, if n and m both are greater than n, then mod Sn minus Sm is equal to, now here we are adding and subtracting S. So that is Sn minus S plus S minus Sm. And if you want to split them, you have to take less than or equal to symbol. Less than or equal to mod Sn minus S plus mod S minus Sm. So this is less than, this is 1 by 2 and this is 1 by 2. 1 by 2 plus 1 by 2 is, or you can take this is epsilon by 2 and this is epsilon by 2. So epsilon by 2 and epsilon by 2 will become epsilon. This is epsilon by 2, which is equal to epsilon. So what did we conclude? That mod Sm minus Sn is equal to epsilon. Therefore, you can say Sn is a Cauchy sequence. This question will come as short answer. Now take this question. This is a long answer type question. Show that a sequence is a convergent sequence if and only if it is a Cauchy sequence. So whenever if and only if is given, you have to prove it in both the ways. Like you have to show that a convergent sequence is a Cauchy sequence, and then you have to show its converse, that is a Cauchy sequence is a convergent sequence. So first let us prove it as convergent sequence is a Cauchy sequence. So for this we have to write the last SAQ. Like this part you have to write it again. So let limit Sn is equal to S and let epsilon greater than 0, then there exists capital N which is positive such that n is greater than n, which implies mod Sn minus Sn is less than epsilon by 2. Clearly we are taking small m which is greater than n. Then again you can write this as Sm minus S is less than epsilon by 2. So therefore if n and m both are greater than n, then how can we write mod Sn minus Sm? We are adding and subtracting S and then we are splitting it. So we got it as epsilon by 2 by epsilon by 2, that is epsilon. So we got that mod Sm minus Sn is equal to epsilon. Now the second part is you have to show that Cauchy sequence is a convergent sequence. So now let us say Sn is Cauchy. So sequence Sn is bounded. So we only need to show that limit infimum Sn is equal to limit supremum Sn. Now for epsilon greater than 0, there exists n greater than 0 such that if m comma n greater than n, which implies mod Sm minus Sn less than epsilon. So to remove this modulus, we need to take Sn less than Sm plus epsilon. We are taking Sm that side, okay? For all m and n greater than n. Which implies Sm plus epsilon is an upper bound. Is an upper bound for the sequence Sn such that n greater than n. Here colon means such that. Now we take Vn. Vn is equal to supremum of Sn such that n greater than n less than or equal to Sm plus epsilon for all n comma m greater than n. Now we will subtract each side with epsilon. So we get Vn minus epsilon less than or equal to Sm for all m greater than n, which implies Vn minus epsilon less than or equal to, what is Sm? Sm is infimum of Sm. Infimum of Sm such that m greater than n. which is equal to un. Infimum we are denoting by un, supremum we are denoting by vn. So which implies limit supremum Sn is less than or equal to Vn is less than or equal to Un plus epsilon less than or equal to limit infimum Sn plus epsilon. So therefore you can say that limit supremum Sn is less than or equal to limit infimum Sn. Hence proved. This is the condition of convergent sequence. Now take this problem. This is very, very important. Let Sn be an increasing sequence of positive numbers and define sigma n equals 1 by n into S1 plus S2 plus so on up to Sn. Prove sigma n is an increasing sequence. So first let us write down what is given to us. So given that Sn is an increasing sequence of positive numbers. And sigma n is equal to 1 by n into S1 plus S2 plus so on up to Sn is given. So this problem can be proved by induction. The given problem can be proved by method of induction. Induction means mathematical induction. Now let us consider 0 less than S1 less than or equal to S2. Thus, S1 plus S1 is less than or equal to S1 plus S2. So we have added S1 on both sides. So S1 plus S1 will become 2S1 less than or equal to S1 plus S2. If I take 2 to the other side, S1 less than or equal to S1 plus S2 by 2. Therefore, it is true for n is equal to 1. Now in mathematical induction, we will do it in 3 steps. First, we will prove it for n is equal to 1. Then we will prove it for n is equal to k. And then we will prove it for n is equal to k plus 1. So the first step is completed. That is, we have shown that it is true for n is equal to 1. Now we will assume it for k and we will again prove it for k plus 1. So let sigma k is true. Sigma k means in the place of n we put k. So S1 plus S2 plus so on up to Sk by k is less than or equal to S1 plus S2 plus so on up to Sk. We are adding k plus 1 here. And Sn is greater than or equal to Sj for all j less than n. This symbol is for all, remember. So which implies S1 plus S2 plus so on up to Sk plus 1 is less than or equal to Sk plus 1 plus Sk plus 1 plus so on up to Sk plus 1, where there are k plus 1 summands. Summands are the terms which are added. So there are k plus 1 terms which we are adding. So 0 less than or equal to Sk plus 2 into k plus 1 minus S1 minus S2 so on up to minus Sk plus 1. So we are subtracting them. So therefore S1 plus so on up to Sk plus 1 by k plus 1 less than or equal to S1 plus S2 plus so on up to Sk plus 1 by k plus 1 plus sk plus 2 into k plus 1. Then again we are subtracting all the terms. Minus s1 minus s2 minus sk plus 1 by k plus 2 into k plus 1. So if you further simplify this, you will get k plus 2 into, we are taking LCM now. So k plus 2 into s1 plus s2 plus so on up to sk plus 1 into sk plus 2 into k plus 1 minus s1 minus s2 so on up to minus sk plus 1 whole divided by k plus 2 into k plus 1. So we have taken LCM in this step. Now now we will multiply S1 into K plus S2 into K plus 1. Each term we are multiplying with K plus SK plus 1 into K. Now each term of this bracket we are multiplying with 2. First we multiplied with K, now we are multiplying with 2. So that is 2S1 plus 2S2 plus so on up to 2sk plus 1 plus sk plus 2 into k plus 1 minus s1 minus s2 minus so on up to minus sk plus 1 whole divided by k plus 2 into k plus 1. Or you can write k plus 1 into k plus 2. Both are one in the same. Now what is left over? So S1 if I take common, we will get k plus 1. Then S2 if we take common, we will get k plus 1. Then Sk plus 1 if we take common, we will get k plus 1. And then Sk plus 2 if we take common, we will get k plus 2. Whole divided by k plus 1 into k plus 2. So in all the terms you have k plus 1. So if we take k plus 1 common, you will get k plus 1 into S1 plus S2 plus so on up to Sk plus 1 plus Sk plus 2 whole divided by k plus 1 into k plus 2. Now k plus 1 cancel. You get S1 plus S2 plus so on up to Sk plus 2 whole divided by k plus 2. That is nothing but sigma k plus 2. So therefore, we can say S1 plus so on up to Sk plus 1 by k plus 1 is less than or equal to S1 plus S2 plus so on up to Sk plus 2 by k plus 2. So finally you can conclude, therefore sigma n is an increasing sequence. So this is the condition for increasing sequence.